Good morning. Today we will study some basic concepts of inner product space and Hilbert space. So what is inner product? An inner product on X is a mapping of Cartesian product of X with X into a scalar field K of X, so that every pair of vectors X and Y belonging to X, there is associated a scalar which is written like this and is known as inner product of X and Y, such that for all X, Y, Z belonging to X and scalar alpha belonging to K, we have inner product of X plus Y and Z equal to inner product of X and Z plus inner product of Y and Z. Inner product of alpha X and Y is equal to alpha times inner product of X and Y. Inner product of X and Y is equal to conjugate of inner product of Y with X. Inner product of X and with X is always greater than equal to 0, and inner product of X is with X is equal to 0 if and only if X is equal to 0. It is 0 here. So if all the four properties are satisfied, then this representation denotes the inner product of X and Y, and it is a mapping from X cross X to a scalar field K. An inner product on X defines a norm on X, which is defined as norm X equal to square root of inner product of X and X, and it also defines a metric given by distance between X and Y equal to norm of X minus Y. This we define in the norm space also, and it is equal to square root of inner product of X minus Y with X minus Y. So in a sense, inner product spaces are norm spaces and Hilbert spaces are Banach spaces. So inner product space is a vector space with inner product of X and Y defined on it. It is also called pre-Hilbert space. And Hilbert space is a complete inner product space. It is complete in the metric defined by the inner product, which we have defined like this. Metric on Hilbert space is defined like this: distance between X and Y is equal to square root of inner product of X minus Y with X minus Y. Here you have noticed that we have written bar. Bar means the complex conjugation. If X is a real vector space, then we will simply have inner product of X and Y equal to inner product of Y with X. Here we don't have bar in this case if the space is real, and it shows the symmetry. So our these first three formulas can be used to obtain inner product of alpha X plus beta Y with Z is equal to alpha times inner product of X with Z plus beta times inner product of Y with Z. Inner product of X with alpha Y here is equal to conjugate of alpha times inner product of X and Y. Notice that here alpha was on the left side. So inner product of alpha X and Y is equal to alpha times inner product of X and Y. But here alpha is on the right side. So in this case, inner product of X and alpha Y is equal to conjugate of alpha times inner product of X and Y. If we have alpha this side, then we will have alpha bar here. Inner product of X and alpha X with alpha Y plus beta Z is equal to alpha bar inner product of X with Y plus beta bar inner product of X with Z. So this first property shows that the inner product is linear in the first vector, because in this case this is, although it is somewhat like linear, but it is not completely linear, because here we have alpha bar and beta bar, which are complex conjugates of alpha and beta respectively. So it means we say that inner product is conjugate linear in the second vector. We call it conjugate linear. This we call linear in the first vector. It is complex conjugate in the second vector. So expressing both the properties together, we say that inner product is sesquilinear. Sesquilinear means it is 1.5 times linear. So 1.5 times linear is motivated by the fact that conjugate linear is semi-linear or half linear. So because it is 1.5 times linear, so we call it sesquilinear. In norm spaces, we can add vectors, multiply vectors by scalars, just as in elementary vector algebra. Further, the norm on such a space generalizes the elementary concept of length of a vector. However, what is missing in general normal norm space? What would like to have, if possible, is an analog of the familiar dot product. How we find dot product? In vectors, a dot b is equal to alpha 1 beta 1 plus alpha 2 beta 2 plus alpha 3 beta 3. If a is equal to alpha 1 I plus alpha 2 j plus alpha 3 k, b equal to beta 1 I plus beta 2 j plus beta 3 k, then a dot b will be like this. And modulus of a is equal to square root of dot product of a with a. And the condition for orthogonality is a dot b equal to 0. It is also called the condition of perpendicularity. So it generalizes the dot product of vectors in 3-dimensional space and is used to define norm, which we have defined like square root of inner product of x with x. Also orthogonality by inner product of x with x is 0. So the theory of inner product and Hilbert space is richer than the general norm space and Banach space. So what is different in Hilbert space? In Hilbert space, distinguishing features are representation of H as a direct sum of closed subspace and its orthogonal complement. Second, orthonormal sets and sequences and corresponding representation of elements of Hilbert space H. There is representation of bounded linear functional by inner product space, by inner products. Last one is Hilbert adjoint operator T star of a bounded linear operator T. Hilbert adjoint operators can be used to define classes of operators like self-adjoint, unitary and normal. Also, norm on an inner product space satisfies the parallelogram equality. Norm x plus y whole square plus norm x minus y whole square equal to 2 twice norm x whole square plus norm y whole square. This is a diagram which represent parallelogram equality. This is vector x, this is vector y, and this is vector x plus y, and this represents x minus y. We know that norm generalizes the elementary concept of length of a vector. So such an equation continues to hold in our present situation in much more general setting. We conclude that if norm does not satisfy the above equation, it cannot be obtained from an inner product by the use of 1. So not all norm spaces are inner product spaces. Also we know that if the dot product of two vectors in 3-dimensional space is 0, then the vectors are orthogonal, or we can say they are perpendicular, or at least one of them is 0 vector. So what is orthogonality? An element x of an inner product space capital X is said to be orthogonal to an element y belonging to x if inner product of x and y equal to 0. We also say that x and y are orthogonal, and we write x is orthogonal to y like this. This is the symbol of like perpendicular also. Similarly, for sets A and B, which are subsets of X, we write x is orthogonal to A if x is orthogonal to A for all A belonging to A, means for all the elements of the set A. And two sets are said to be orthogonal if its each element is orthogonal, means A is orthogonal to B for all A belonging to A and all B belonging to B. Now we will discuss some examples of Hilbert space. The Euclidean space Rn is a Hilbert space in which we define inner product as xi1 eta 1, xi2 eta 2, xi n eta n, where x is equal to xi1, xi2, xi n and y is equal to eta 1, eta 2, eta n. In fact, norm x is equal to inner product of x with x and its square root, which is equal to xi1 square, xi2 square, xi n square under root. And we define the metric on Euclidean metric like this: norm x minus y equal to inner product of x minus y with x minus y, and on simplification it will come out to be xi1 minus eta 1 whole square, xi2 minus eta 2 whole square, and so on up to xi n minus eta n whole square and under root. And this Euclidean space Rn is complete Hilbert space. If instead of n we have n equal to 3, then this formula will reduce to inner product of x with y equal to x dot y, and it is equal to xi1 eta 1, xi2 eta 2, xi3 eta 3. Here x is equal to xi1, xi2, xi3 and y is equal to eta 1, eta 2, eta 3. And x and y are orthogonal if inner product of x with y equal to x dot y, and which is equal to 0. In case of unitary space Cn, here C is the set of complex numbers. The space Cn is a Hilbert space with inner product defined like this. Here inner product of x and y is xi1 eta 1 bar plus xi2 eta 2 bar plus xi n eta n bar. We obtain the norm defined as norm x equal to xi1 xi1 bar, xi2 xi2 bar, xi n bar and square root. Or in on simplification we will get modulus of xi1 square, modulus of xi2 square, modulus of xi n square under root. And the space L square AB is also a Hilbert space. In this case we define norm x equal to integration of xt square with respect to t within the limits a and b and its square root, and xt bar is equal to modulus of xt square. Xt bar is conjugate of xt, and this can be obtained from the inner product defined like inner product of x and y is integration of xt with yt within the limits a to b, and we are integrating with respect to t. These functions form a complex vector space which becomes inner product space if we define inner product of x with y as xt yt bar integration of xt yt bar with respect to t within the limits a to b. Here bar denotes a complex conjugate. This space is also complete. Thank you.